Hi everyone. In this video we're going to discuss cosets. So the idea here is to start with a group G and a subgroup H, and then study the translates of H in G. You can sort of draw a picture of this as follows. So imagine G, our group, as sort of being this square, and H living inside of G. So there's H. And we're going to sort of just smear H around within G. Those are going to be called translates or cosets of H in G. So this study is more than just interesting in its own right. It turns out that it leads to some important consequences. First of all, there's this theorem called Lagrange's theorem, which says that if you start with a finite group G and a subgroup H, then the size of H must divide evenly into the size of G. For instance, if the order of G is 10, then what this means is that G cannot possibly have a subgroup, say, of order 7, because 7 doesn't divide evenly into 10. Also, this study of translates or cosets is going to give rise to a new type of group construction called quotient group. So now it's time for us to become a bit more specific about what we mean by these translates of H within G. So we let H be a subgroup of G, and we fix an element A in G. We say that the right coset of H by the element A is this set, which we denote HA, and it consists of all of the things in H multiplied on the right by this fixed element A. So you can do the same thing, similar thing, for what are called left cosets. So the left coset of H by A is this A times capital H, and that's a new set that means that we take everything in H and we multiply it on the left now by A. Now sometimes in our group G we have sort of an additive operation, and if that's the situation, then our notation for cosets becomes a little bit different. So instead of HA for a right coset, we would instead write H plus A. And similarly for left cosets, we would write A plus H. So now we begin a series of examples illustrating some ideas about cosets. Here our group G is going to be the cyclic abelian group Z8. And H, a subgroup of G, is going to be the cyclic group generated by 2. And that just consists of these elements 0, 2, 4, and 6. So what we're going to do is just list the left and right cosets of H and G. So here in the middle of the slide, we see the right cosets of H. So we can begin by taking H here and just adding 0 to every element of H on the right. So that really doesn't have much effect on H. We take 0 plus 0 to get 0, 2 plus 0 to get 2, 4 plus 0 to get 4, and 6 plus 0 to get 6. And that yields exactly what we started with. Now we can also take the right coset of H by 2. So the point there is we take everything in H and we add 2 on the right. So 0 plus 2 is 2, 2 plus 2 is 4, 4 plus 2 is 6, and 6 plus 2 is 8, which is really 0 in Z8. So these elements are in a different order, but it really is just the same set as H plus 0. And in a likewise manner, we can compute H plus 4 and H plus 6. Now going over to the right column, if we take the coset H plus 1, there we obtain a different set. So here the point is we take everything in H and we add 1 on the right. So 0 plus 1 is 1, 2 plus 1 is 3, 4 plus 1 is 5, 6 plus 1 is 7, and we wind up with the set 1, 3, 5, 7. And you might observe that we'll wind up with exactly that set, though possibly in a different order, if we take the right coset H plus 3 or H plus 5 or H plus 7. Okay, so there are just a few observations about this calculation that we've made. First of all, the problem asked us to compute the left cosets as well, and perhaps you've already guessed that in this instance, the left cosets and the right cosets are exactly the same because this group is abelian. For instance, if you're going to compute H plus 6 or 6 plus H, the only difference is whether you add 6 on the left or 6 on the right, and that will make no difference because this group is abelian. So these two are equal. Okay, another thing you might notice is that really there are only 2 distinct right cosets here. The set 0, 2, 4, and 6. And this set 1, 3, 5, and 7. So H and H plus 1 are really the only 2 distinct cosets there are, or that you could call them H plus 2 and H plus 5, however you like. So anyway, what you might notice about these 2 sets is that they are disjoint. First of all, there's nothing in common among them or between them. And if you take the union of those sets, you get all of G. So what that means is that these distinct cosets partition G. So that takes care of our first observation. And we've already mentioned the second one, that is that the left cosets are equal to the right cosets. And then another thing you might notice is that if you have 2 right cosets that are equal, like for instance H plus 3 and H plus 5, those give you the same set. Then if you look at, say, 3 minus 5, which is minus 2, which I guess is 6 in this group, that 6 is an element of H. And in fact, that's not a fluke. If you take if you have 2 right cosets that are the same and you take the difference of the so-called representatives, A and B, that difference is always going to lie within the subgroup H. Well, now let's try another example, but this time let's use a group that's non-abelian. So here our group is going to be the symmetric group S3, which we learned about in the last video. And remember, its shorthand is EF, F squared, G, F, G, and F squared G, where F is this 3 cycle, 1, 2, 3, and G is the transposition that sends 2 to 3, and vice versa. Now our subgroup H is going to be the cyclic group of order 3 generated by F. And what we're going to do is compute the cosets of H in S3. So this time, as opposed to the last slide, we're going to write down exactly what the left cosets are. So again, H consists of the identity F and F squared. And, if we take the left coset of H by E, we just get H again, and we already know what that is. We can also multiply H on the left by F. So that means we're taking everything in H and we're multiplying it on the left by F. And when we do that, you might see that we get exactly the same things that we started with. We get F, F squared, and E, which is exactly the same set as H. And we can also multiply everything in H on the left by F squared, which again gives us f squared, E and F, which is exactly the same set as H. Now we start to get different things in the right-hand column. So now if we multiply everything in H on the left by G, well, G times E is just G. G times F is GF. And G times F squared is, well, GF squared. Now, remember, though, that in S3, GF and F squared G are identical. And that's why we list this as F squared G. And likewise, GF squared is the same as FG. And so that's where this FG is coming from. And likewise, we can compute the left coset of H by the element FG, which entails taking everything in H and multiplying on the left by FG. And you should see that we wind up with these three entries. And those are the exact same entries that we wound up when we took the left coset of H by G. Okay, so we wind up with these 6 left cosets of H in G. And what you might do now is pause the video and see if you can compute the right cosets of H in G. And what you might find out after you do this computation is that you get the exact same sets. That is, the left cosets are equal to the right cosets. Okay, and that was similar to something that happened on the previous slide. And now in the first bullet point, again, you might notice that we have 6 left cosets, but really if we're just looking at distinct sets, we have this one and that one. So there are really only 2 distinct cosets. And together, those sets partition the whole group S3, meaning that they are disjoint, and their union makes all of S3. And then finally, if you have 2 left cosets that are identical, you might notice that if you take the inverse of the first representative and multiply it by the second representative, you wind up with an element of H. And I'll let you test that for yourself. So in our final example, again, we're going to be talking about the symmetric group S3, which again is given in this shorthand form using E's, F's, and G's, where F is the 3-cycle 1, 2, 3, and G is the transposition 2, 3. Now, unlike the last example, our subgroup this time, instead of being generated by F, is going to be this subgroup K, which is generated by G. And we're going to consider the cosets of this subgroup K inside of S3. So first of all, because G is of order 2, the subgroup generated by G is just going to have 2 elements in it, namely E and G. So now we go ahead and list the left cosets. So K is just K. There's nothing to do there. If we take G times K, that means we're taking everything in K and we're multiplying on the left by G. And if we do that, we get G times E, which is just G. And then we get G times G, which is G squared, but G squared is the identity. So we wind up just with K again. And then we come up over here to the middle column and take FK. So there we're taking everything in K and we're multiplying on the left by F. And that gives us F and FG. And likewise, this left coset gives the same thing. And then we just continue to compute left cosets, and we wind up with these sets. Now, you might notice that there are really only 3 distinct cosets, namely these 3 that I'm circling right now. You might notice that those cosets are all disjoint, and that if you put them all together, you get the entirety of S3. So there are three distinct left cosets, and they go together to give S3. Now here we're also going to compute the right cosets. So we start with K. There's nothing to do there. And then for the right coset KG, well, we multiply everything on K, this time on the right by G, and we wind up with, again, G comma E. And so at this point, we might be thinking, well, this is the same old story where the right cosets and the left cosets were all sort of equal to each other. But it turns out that that does not happen here. And the first place where you can probably see that is when we look at the right coset KF compared with the left coset FK. So KF, what happens there? We're taking everything in K and we're multiplying on the right by F. So E times F is just F. G times F, what's that? Well, we know that that's the same as F squared G. That's where the F squared G comes from there. But now you compare it with the left coset FK, and you might notice that these two sets here, those two sets there, they are not the same set. Okay? So the left cosets are not equal to the right cosets in this instance. Now again, you can check these sort of conditions that two left cosets AK and BK are equal if and only if A inverse B actually sits within K. And then there's a similar condition for right cosets, that KA equals KB, but this time that's true if and only if A times B inverse is in K. So you might take a moment, maybe pause the video and check a few examples to make sure that those two conditions really are holding. Okay, now we're going to use those previous examples to try to motivate some general properties about cosets. So the first thing we're going to do is start with a group, capital G, and a subgroup, capital H. And we can use those two to define a relation on the set G as follows. So we'll say that A is equivalent to B if and only if A inverse B sits within the subgroup H. So this relation, it turns out, is an equivalence relation on G. Now in your reading, there's quite a bit more about equivalence relations, and I'll ask you to read through some of that material. I will not be reviewing it in great depth here. Okay, but that's item one of our theorem, is that this relation is an equivalence relation. And then the second part of our theorem says that if we start with a group element, say A, and we let A bar denote the equivalence class containing A, then this equivalence class is actually equal to the left coset of H by A. So this means that the equivalence classes for this relation, this equivalence relation, are exactly the left cosets of H and G. And that turns out to have important consequences. Okay, well, why don't we try to prove this theorem? In fact, we'll go ahead and prove part one, and that might help us review a few things about equivalence relations. So remember, an equivalence relation is a special relation that has three properties. The first thing that it has to be is it has to have a reflexive property. That means we require that anything be equivalent to itself, right? And that's true because A inverse times A is the identity. And remember, every subgroup contains the identity, right? So the second thing that we need for an equivalence relation is a symmetry property. That is, if, suppose, you know, we have A being equivalent to B. And so if A is equivalent to B, we want to show that B is equivalent to A, right? So this says that A inverse B is in H. So because H is a subgroup, I know that the inverse of this thing must also lie in H. And that inverse, remember, is B inverse times A. But remember, B inverse A lying in H, that's the same as saying that B is equivalent to A. Okay, so therefore this, this relation has a symmetry property. Now finally, there's this transitive property that needs to be satisfied, right? So let's suppose that A is equivalent to B, and B is equivalent to C. Then, what is it? A inverse B and B inverse C both lie in H. And then because H is a subgroup, we know that the operation on H is binary. And so when I multiply these together, A inverse B times B inverse C, I get A inverse C also lying in H. So A is equivalent to C. And that's the transitive property. Here now we see this same theorem again. And this time we're going to prove part 2. That is, we're going to show that the equivalence classes of this equivalence relation are exactly the left cosets of H in G. So this will require us to remember what's meant by an equivalence class. So this object, A bar, this is a set, and it consists of all of the things in G that are equivalent to A under this equivalence relation. So I want to show that those two sets, A bar and the left coset AH, are equal. And that means that I need to show that a generic element of one lies in the other and vice versa. So let's start with an element B that's in A bar. Well, that happens if and only if A is equivalent to B, right? Remember, A bar consists of everything that's equivalent to A, and so we know that B must be equivalent to A. But that is the same thing as saying that that's the same thing as saying that A inverse B sits within H. And that's the same thing as saying that A inverse B is equal to some little h for some little h in capital H, which is the same thing as saying that B is equal to little a times h, right, for that same h. And that's equivalent to saying that B is in the left coset A times capital H. Right? Remember, A times capital H is the set of all things that you obtain by multiplying things in H on the left by A. And so indeed, B has that form. We've taken something in H and multiplied it on the left by A. And so B is a member of this left coset. And so at the end of the day, we see that something sits within the equivalence class if and only if it sits within the left coset. And so that means that the two sets are equal. This theorem we've been discussing has an important consequence. And to understand that, I want you to remember that when you have an equivalence class or an equivalence relation on a set, and you look at the equivalence classes, those equivalence classes will always partition the set, meaning that you can express that set as a disjoint union of equivalence classes. Now, in this particular instance, we've just shown that the equivalence classes on G are in fact the left cosets. And so what that means here, importantly, is that the left cosets of H partition G. And even more than that, what you might have noticed from the examples, and what is not extremely difficult to prove, is that all of these cosets are exactly the same size. In fact, they're each the size of the subgroup H. So that means that these left cosets of H partition the group G into sets of equal size, namely the size of H. And what that means in particular is that if you look at the size of H, it must divide the size of G for finite groups. And that's really important. It means that if you're looking around for subgroups, of a group of order 12, then you're not going to find any subgroup of order 7 because 7 doesn't divide 12. Okay, and we'll be talking a lot more about that in the next video. So this theorem that H, the size of H divides the size of G, that's a theorem called Lagrange's theorem. It has a lot of interesting consequences. Okay, now a lot of this discussion about this theorem has involved left cosets and an equivalence relation involving these left cosets. But you can have this same conversation about right cosets, although you need to change the equivalence relation a little bit. So the analogous theorem holds for right cosets as well.